Okay, excellent. Yeah, the recording has started. Okay, so it's a great pleasure to have Sean Hartnell speaking to us from Stanford. He is going to tell us about bootstrapping matrix quantum mechanics. I will forego further introductions because we're running late. Thanks, Sean, for agreeing to give this seminar.
No, that's my pleasure, and thanks for I guess it's the evening time for you guys. So thanks for finding the time. That's right. I want to talk about a preprint we put out recently called Bootstrapping Matrix Quantum Mechanics. And I don't have a lot of slides, so there's plenty of time if there are questions and interruptions. That's all fine. We're not in a rush. Well, I don't know if you've had dinner yet, but anyway, as far as the talk goes, we're not in a rush. Okay. So these are with a couple of collaborators. Sija is my graduate student here at Stanford, and Yoret is a postdoc. And the work I'm going to talk about is in this paper on the arXiv. Very good. So let me just spend a little bit of motivation, and like I said, really, please, questions at any time are very welcome. So, we find ourselves living in space, right? That's unavoidable. However, I think at this point, it's fairly clear that this space that we find ourselves in is not perhaps a fundamental physical thing, but is rather emergent from some more fundamental or possibly dual microscopic description, which doesn't involve space explicitly. And the reason I say it's quite clear is that while we don't have a theory of quantum gravity in the real world, we do have quite sophisticated models where we can really see that happening, right? We're in holographic duality, there are really cases where you just start with a theory that does not have space, and then you look for what the excitations of that theory look like, and you see that it's as though they live in a space. Okay, so in particular, the kind of theories that do that are quantum mechanical theories of large N matrices. Okay, and we'll do a few examples of this in a minute. The most famous of these is actually more than a quantum mechanics, is even a quantum field theory. So the most famous, I guess, at this point is this N=4 super Yang-Mills theory, which is a gauge theory that lives in 3+1 dimensions, but describes a space-time in more dimensions. But really the essence of all of these models is that they have the degrees of freedom are large N matrices in the way that we'll talk about. And so it's understood at this point that large N matrices can produce a semi-classical and gravitating space-time that isn't there to begin with. Right? So you don't put the space in, or you put in the large N matrices, and the space is something that comes out. Now, while we're pretty confident that this happens in some cases, I think it's definitely fair to say that we don't really understand how that happens. Okay, somehow there are many degrees of freedom, and they're very big matrices, but these degrees of freedom have to be able to rearrange themselves to establish a locality, a spatial locality that wasn't there to begin with. And I think it's pretty clear that we don't really understand how that happens. And I'm particularly fond of this case of matrix quantum mechanics that I'm going to tell you more about in a minute, because there's just no space to begin with. There's only time. Okay, it's literally a quantum mechanics. So let's see, what am I going to say next? Yeah, right. So matrix quantum mechanics is literally an undergrad quantum mechanics where you have a very large number of coupled harmonic oscillators. That's essentially what it is, with a bit more structure. And there's definitely no space anywhere. There's just a lot of coupled harmonic oscillators, and space has to emerge. This is unlike this case of some field, like N=4 super Yang-Mills, or some field theories where you have some space to begin with and some space grows. Okay, in a matrix quantum mechanics, the entire space is emergent. Okay, so all the space must emerge. And there's no locality built in to begin with, only time. Okay, so to understand how space emerges from large N matrices, one would like to be able to solve these matrix quantum mechanical theories. All right, and so this talk is not going to be about emergent space. This is a motivation. This talk is going to be about solving matrix quantum mechanics theories. I'm going to define a few in a minute. All right. So there are many, matrix quantum mechanics comes in many flavors. the simplest and the main organizing principle is how many matrices you have. Okay, and I will write down some Hamiltonians, of course, in a minute. The simplest is a single matrix. Okay, so this is, maybe I can say now what this is. So imagine you have a Hamiltonian. So let's say you start with a harmonic oscillator, right? Then you'd have like a p squared plus x squared. Okay. Now suppose you have a second harmonic oscillator, q squared plus, actually let's call it p1 squared, sorry, p2 squared plus x2 squared. Okay, now you have two harmonic oscillators and you could couple them. Okay, suppose you repeat this process, but instead of two harmonic oscillators, you have a whole bunch of them. In fact, you have n squared harmonic oscillators, okay? And then you imagine all of those oscillators filling out a matrix, and then you write down certain couplings that you can write as traces, powers of traces of this matrix. And it turns out that has an SUN symmetry, and you can do a lot with it, okay? So that would be the theory of by a single matrix, I just mean n squared harmonic oscillators that are coupled in a certain way. Okay, so these such theories can be solved exactly. And the nice thing about having just one matrix is you can diagonalize it. And then it turns out, I'm not going to review this, but it was well understood in the 90s and even earlier, that the single matrix, you can diagonalize it, and the eigenvalues, the quantum mechanical problem you're solving becomes a quantum mechanics of free fermions in some potential. Okay, and this was studied to death in the 90s, and it plays an important role in two-dimensional string theory. Okay, so I'm not going to give very many references in this talk. Please, if there happens to be anybody who I'm not referencing, including my host, don't take it personally. But there's a lot of work in the 90s. I'll try to mention it as I go along. There's a lot of work in the 90s solving this one matrix case. Okay, so that's solved. And actually, there is an emergent space. Okay, but the space is a little bit boring. What you get is that the eigenvalues spread out and form a one-dimensional space. Okay, so starting from one matrix, the eigenvalues sort of spread out and build a one-dimensional space for you. But we'd really like to have higher dimensional spaces than just one dimension. And in particular, there are a lot of things that are a bit particular to one dimension that one would like to go beyond. Okay, so to go beyond more than one emergent dimension of space, you need more matrices. And so let's go to the other extreme. So the richest matrix theories are these so-called BFSS theory and the BMN theory, which is a version of it. These have many matrices. They have 9 bosonic matrices and a whole bunch of fermions. And they're special because these are maximally supersymmetric models. So they have the most number of symmetries they could possibly have. And they're important for a microscopic definition of M theory. Okay, so here's one matrix. This would be 9 matrices plus fermions. Okay, at the moment, that's going to be too difficult, but that's where one would like to head, right? So a goal, clearly an important goal. At some point, if we want to understand space, we will have to really just solve these BFSS matrix quantum mechanics, but we're not there yet, but that's where we're heading. So there are many theories in between one matrix and 9 matrices. There are many other theories. So you can vary the number of matrices, and you can also vary the degree of supersymmetry. And the state of the art is that at the moment is that very, very, essentially nothing is known about theories with more than one matrix, okay? In case for people who have thought about these things, there are also matrix integrals, and that's not what I'm talking about. Matrix integrals don't involve time, okay? I'm talking about quantum mechanics that does have a time in it. So there are cases of matrix integrals with 2 matrices that you can do, but matrix quantum mechanics with 2 matrices is currently not solvable, okay? So the first baby step we want to take is to solve matrix quantum mechanics with with 2 matrices. Okay, so that's what we're going to be doing. Okay, is that any questions about that? I know it's mostly just words at this point. Okay. Okay. So I should say that one reference I do want to give is that this work I'm about to talk about was directly inspired by a beautiful paper by Henry Lin, who's actually is a graduate student at Princeton, I believe. And he showed how you could solve large N matrix integrals. Okay, so a matrix integral, there's no quantum mechanics, there's no time. It's just an integral over a matrix, right? And you might, the simplest matrix integral would be something like this, right? Some matrix over matrix M. But of course, you can also have non-Gaussian integrals. And Henry showed how you can solve these kind of integrals using methods similar to what I'm about to tell you about, using positivity constraints. So what we're going to do is use the same philosophy, but for matrix quantum mechanics, which is a little bit more complicated. And the strategy is going to be the following. But again, the quantum mechanics is just like undergrad quantum mechanics. Okay, there's no quantum field theory, no string, nothing fancy. It's just quantum mechanics with a lot of oscillators. Okay, and the strategy is the following. We're going to relate the expectation values of simple operators to those of long operators. So we're going to establish relationships between expectation values in the ground state, actually any eigenstate, and then there are going to be certain positivity constraints on the sort of longer operators that are going to be seen, that will strongly constrain the simple operators. Okay, and the bootstrap, what the bootstrap is it's a whole program that's been very successful in the last few years, mainly for things like conformal field theories, where you basically scan over all possible values of some parameter that you care about, and you exclude almost all the values because they violate some kind of positivity constraint. Okay, and that's what we're going to do here. And so what we're heading to is going to be some new results on two matrix quantum mechanics. Okay, about which once again very little is known. Okay, so the plan, now I get to the substance, we're going to do it in 3 steps. We're going to start by just doing a warm-up, which is we're going to use these bootstrap methods to solve the anharmonic oscillator. Okay, that's just like one textbook quantum mechanics problem. Then we're going to do one matrix quantum mechanics, which I told you is already solvable, but this will check, it'll be a check on our techniques. And then I'll talk about two matrix quantum mechanics, which is not solved. All right, so here's the anharmonic oscillator. So this is really single particle quantum mechanics, okay? There's p squared, x squared, and some quadratic term. All right, so this cannot be solved exactly. It's very, very easy to solve it numerically. You solve Schrodinger's equation, it's simple, but this is how we're going to do it. Okay, so I want to illustrate the bootstrap method on this problem. So there are 2 steps. And so the first step is to establish a recurrence between expectation values. And what we do that is with this equation. It's a very well-known fact. Okay, this is the commutator of the Hamiltonian with any operator in an energy eigenstate is 0, right? And that's just because the Hamiltonian acts to the left, it acts to the right. You get the energy in both cases, so it cancels, right? This is just HO minus OH in some state. And so H can act here, H can act there. You get the energy in both cases and you just get 0. Okay, so let's take that identity and put in these operators, x to the s, x to the t times p for any power s and t. You plug this in, you commute these operators with this Hamiltonian, very, very simple, right? You start commuting stuff around, and with a very, very small amount of algebra, you can show that you get a recurrence relation between expectation values. Okay, so remember, look, this is the expectation value of x to the different powers of x. Okay, they depend on t, and also the energy comes into it. How did the energy come into it? Because when we do this commutators, we're going to be left with some factors of p squared, and to get rid of the p's, because this recurrence relation only involves x's, to get rid of the p operators, we use the fact that the energy of this state is E, right? And so this will allow us to relate the expectation value of p squared to the expectation value of the energy and of the x's, right? And so this is a closed form recurrence relation between expectation values. And so what that means for this problem is that if you know the energy of the state and you know the expectation value of x squared, then you can get all the higher expectation values, okay? But we're going to run it backwards. And so the second step is going to be, we're going to see that there's some constraints on x to the 2t, all right? And so the philosophy is going to be, you guess the energy and you guess x squared, you calculate a whole bunch of higher expectation values, and you see if they're consistent with the constraints or not. If they're not consistent, then that energy and this x squared are not allowed, right? So that's this bootstrap method. Okay, you sort of, you guess the answer and you see if it works, right? So everyone happy with this, right? So this is the recurrence relation. This is good
for. Excuse me. Is this good for any eigenstate, or you're going to work on the ground state?
Sorry. So actually, that's perfect. In this example, we're going to get the whole spectrum. Yeah. So any eigenstates. Yeah, that's right. Yeah, we'll see in a minute. Yeah, but that's right. At this point, I've only assumed it's an eigenstate. Thank you. Yeah, good. And now the constraint we impose this, and this is coming from this paper, is that for any operator O dagger O is a positive operator, and so its expectation value must be positive. And in particular, you can take O to be any sum of powers of X, right? So a simple case would be maybe O is a constant plus C2 times X, for example, okay? So, and we truncate it some K, right? So this is sum of, so this would be the simplest case of K equals 1. And so then you take this operator and you plug it into this constraint, and it's for any C1 and C2. So for example, in this case, this constraint, we could write that as C1, C2, 1 X, X, X squared, C1, C2. This should be positive. Okay, so I'm showing that this constraint, if I put K equals 1, says that this should always be positive, which means that this matrix should be positive. More generally, it means that the K1 by K plus 1 by K plus 1 matrix, this guy should be a positive matrix. Okay? And note that, I mean, so this includes the sort of trivial fact that something like X squared obviously has a positive expectation value. But by allowing these C's could also be negative, right? So this is a stronger constraint than just the diagonal. It's a whole matrix constraint, okay, that we're getting positivities. So this matrix must be positive semi-definite. So in particular, its lowest eigenvalue should be non-negative, okay? So now we get to the bootstrap point. So we do the following. We fix K. This is a numerical method. This is a numerical method. K equals 10, for example. Easily do that on a laptop in a few seconds, a few minutes. You fix K. You get a huge matrix, okay? This matrix, you write down this matrix. You pick a value of E and a value of X squared. You calculate all the higher X's using this recurrence relation. You take this big matrix, you calculate its lowest eigenvalue. If that eigenvalue is negative, then those values of E and X squared are excluded, okay? So we have a positivity constraint on that constrains the energy in X squared, all right? So let me show you what happens. So for example, so this is the energy versus X squared plane, okay? And actually what you get is a whole bunch of islands that are allowed, and that's precisely going to be the spectrum of this model. And just to give you a sense of the convergence, so look, these are like already quite zoomed in. If you look at these numbers, right, I've quite zoomed in. And this is K equals 7, 8, 9. So this is like very fast, okay? I mean, on a computer, and also the trivial to program as well. And so with K equals 7, you get the blue area. Then when you go to K equals 8, it becomes the sort of yellowy orange area. And K equals 9 is the green area. And this red cross is the exact answer, okay, that we know, because it's easy to solve this exactly. Okay, so this is just a warm up. Okay, but this is a way that you could solve quantum mechanics. If you wanted to find the eigenvalue, you don't have to solve the Schrodinger equation. You just impose all these positivity constraints, and you zoom in rather quickly to the eigenvalues. All right, and so actually, and this is the first energy state, right? This is higher energies, and in fact, what you get if you look in the whole plane, if you zoom out a bit, you sort of get a series of dots that look something like this. Now, to get to the higher energy eigenstates, you need a bigger K, right? So this K, it's not that you immediately get the whole thing for free, right? And I would say there's no proof that this converges, but it does seem to converge. And I think that's, I can try to give you a little bit of intuition, actually, that actually also comes from this Henry Lin paper, that roughly, if you, so this may, oh no, I'm sorry, no, that comes later. No, I'm sorry, I jumped the gun. This suggests that somehow these constraints are getting saturated when you take K to infinity, because it looks like you're zooming in on the right eigenvalues. So yes, there's no proof. Sorry, restart. No proof that this method, it has not been, to my knowledge, it's not proven that this method converges, but it does seem to converge. Okay.
In Lin's case, is it known that it converges?
No.
In Henry
no.
Lin's case, not
also
there either.
No. And so that's right. So what he has is this step is basically the same, And but this step is a bit this is a very quantum kind of thing to do, and he does something a little bit different for the integrals. Yeah. Yeah. I don't know. I don't think it's proven. Yeah. Good. Okay. So that's the philosophy. This is the bootstrap, and so you might have seen, if you've seen any other bootstrap talks, and so what these would normally be are things like operator dimensions and CFTs, right? Are what people have been most often applying it to, and so this is just a quantum mechanics.
Can I ask a question?
Yes, please.
This problem has a singularity in the energy has a singularity at G equal to 0. This anharmonic oscillator. It is non-analytic at G equal to 0. How does it show up in this calculation?
Let me see.
The whole result of Bender and Wu and by Barry Simon.
Yeah, I can believe that, because for G negative it's unstable, right? So yeah, that's fantastic. We did not put in negative. I mean, presumably this method will not converge at negative G.
No, it doesn't converge at all. At G equal to 0, it doesn't energy doesn't converge.
Yeah. I mean, these plots are what there is for that question. I mean, it looks like it converges. Let me just see if I can say anything constructive about that. No, I do not have anything insightful to say about that. Yeah,
related question. What you are writing as inequality, this positivity inequalities is I mean, this thing you're writing here, Mij, it is simply what they call, I think, a hamburger moment problem, okay? And Stieltjes moment problem, because you're taking moments of a distribution which is positive. Okay? And there are well-known inequalities. Okay? All the minors should be positive, definite, etc. Where are they? There are nonlinear inequalities on M.
So what's yes, right. Yes.
There are nonlinear. There's a whole host of things which are called, I think, in this case, as the hamburger moment problem.
Okay.
Where are they?
So hopefully these. So let me understand. If I believe that I'm imposing the most of all of these. Very good. So as a constraint on these x's coming from this.
On the m's.
Yes, yes. No, I understand. One second.
Form, no?
Yeah, one second. So I believe that the strongest constraint is that the lowest eigenvalue should be non-negative, right? And so that's the one I'm using. There may be lots of other ones, but I'm not using them.
Okay.
Yeah.
You mean the other ones, if I remember, are that the determinants of submatrices should be positive as well.
Yeah.
That's yes. Actually, that very good. Yes, that of course sounds like it should definitely be true. I mean, in terms of excluding, I don't. Let's see. I haven't thought about whether that will give you more information. Maybe it does, and maybe that would be useful. So we're just imposing what seemed like the strongest constraint, but indeed, maybe these other constraints are also have information in them. That could well be. Yeah.
If I may say, there are actually precise inequalities for the distribution. The distribution, these are moments of a distribution, is Mij. Okay? Here the distribution is given by the expectation value, so mod psi squared. Okay? So there are precise inequalities which are known due to these people on the problem of moments in terms of the moments, in terms of the Mijs you are writing down. There are actually inequalities.
Yeah, sounds great. I could just say this matrix is not going to appear again in this talk. Actually, I'm going to do something different in the higher. But that sounds great. I'd love to. Very happy to be educated about it. So yeah. Actually, if you could possibly write the name in the chat that you wrote, so I can look it up later. That would be.
Okay.
I think you could. That'd be very helpful.
Okay.
Thanks. Very good. Yes. So actually, what is going to come back later? So this, we're not when we get to the matrix quantum mechanics, we're not going to have quite as much of a handle on things, and we won't have a form quite like this one. You'll see. But this question of what happens when the potential is unbounded below is something that we haven't looked at yet, and that is a natural. That is a natural question. I mean, one of these expectations, the states have better be normalizable. So yeah, I said that we get them from E and X squared, but we're also going to use the fact that the expectation value of 1 is 1, right? So the state, we are restricting to normalizable states. That's important. Good. Let's see. Okay, so now let me talk about one matrix. So that was meant to be an illustration of the philosophy. What we're actually going to do is a little bit different. So here's the simple one matrix quantum mechanics. Okay, so there's a p squared, an x squared, and an x to the fourth, and a g, and this g is going to be positive. I don't know what happens as g goes to 0. And let me see. And so this, again, these are n by n matrices, right? Where there's like x11, x12, x21, right? So there's just a bunch of coupled harmonic oscillators. Very good. Of course, you can write down more general potentials. So we're going to take this one. Okay, so the philosophy is the same. There are 2 steps. And so first we want to get relationships between expectation values. And so we're going to use this equation like before, right? That comes from, I guess, time translation invariance, really, this equation. So for example, if we take the operator trace xp and commute it with h, that should be 0. And actually you get this just as an illustration, that's the relationship you'll get between the traces. This is actually just the virial theorem if you take this particular one. Okay. Now, often in these holographic setups, you actually have a gauged matrix quantum mechanics. So we're going to use that. So this thing has an SUN symmetry where you just conjugate the matrices, and that's gauged. To say it's gauged means that physical states must be invariant under this symmetry, should be annihilated by the generators of this symmetry. Okay, so the generators of this symmetry, we can write it like this for this model. This identity term is just because of operator ordering and making sure that the trace is 0. Okay, yeah, because there's a complication now, right? Because there's 2 senses of non-commutativity. There's a matrix non-commutativity, and there's also an operator non-commutativity, right? So this xp, right? This thing is a matrix, right? So G, so there's x a b p b c minus p a b x b c, right? And so they're all, this commutator is ordered like that. But as operators, you'd like to have the x on the other side. But when you commute them, you'll pick up this identity. Okay, anyway, that's a small point. Just what is important is that there's, everything has a matrix index, and every entry of the matrix is an operator, right? So there's 2 senses in which things don't commute. All right, so the fact that this should annihilate physical states, we actually don't need this trace here, but we'll put it there. And so G should annihilate the physical state, and so G times any operator, its expectation value should be 0. And the simplest case of that is that trace of G should be 0. And so that's one example. That's the simplest example. And also, if we go back to here and put O equals x squared, I'm doing that. So if you can combine, it's just an example. This is requiring SUN invariance. This is sort of an example of that. If you combine those, you see that symmetries that you fix this trace xp expectation value. Okay, so you put these are all very simple manipulations, right? You put the Hamiltonian in here, you put this in there. It's clear that this G, right? This G, you're going to get expectation value of xp, expectation value of px. You get similar things from here, and that allows you to fix both of them. Okay, so I'm just illustrating how these identities relate or fixed expectation values of traces of this matrix. Right? Very similar to before. Okay. Now, what's going to be not as nice as before is in the single particle case, we could eliminate the momentum, right? I gave you this closed form recurrence relation just for the x's. And that's because whenever we got 2 p's, a p squared, we could use the Hamiltonian to eliminate it. But here, because there are lots of this matrix structure, you might get operators like trace, I don't know, x, p, x squared, p squared, x, whatever. That's some operator, right? And you're not going to be able to move all the p's, whilst the Hamiltonian only has trace p squared in it. And so hopefully it's clear that when you start applying these constraints, you're not going to be able to eliminate all the p's using the Hamiltonian, because the momentum operators appear in more complicated ways, and so you're just stuck with them. So we're gonna keep the momentum operators this time, all right? And they're gonna be part of the bootstrap. So for example, so the philosophy is we take a selection of operators and you write down a matrix that's non-negative, similar to before. So here's a baby example. Suppose we have I, the identity x squared, x, and p. Okay, those are 4 operators, and we build this matrix. And so this matrix of expectation values has to be a positive matrix from this identity, the same identity as before, where we take O to be, trace of this has to be positive. And so we take O to be a general superposition, a general sum of these 4 operators. And that this identity implies that this matrix has to be positive now. Okay, so it doesn't quite have the same structure as before. And so, right. And so you just calculate the you ask the smallest eigenvalue of this matrix be positive, and that gives you some constraint between these expectation values. Also in the previous slide, I showed you that I know x and p, and I know p squared in terms of x squared and x to the 4th, right? So this p squared here, I can eliminate it. This one I can eliminate, that one I can eliminate. This one is 1, right? And then I'm going to get the constraint only in terms of x squared and x to the 4th. And so positivity of this matrix implies I can eliminate some of the variables. And so for example, positivity in this simple case ends up implying this. All right, so this is some constraint on trace x squared and trace x to the 4th, and now depends on G, right? Because I used this virial theorem. Okay, so again, what I'm trying to show you is that basically take a selection of operators, of strings of x's and p's, build a matrix out of them that has to be positive. That's these expectation values, okay? And then use all possible relationships between operators that I can find, and then write down the positivity constraint, and then I get some positivity constraints, yeah? This is a baby example. So more generally, what I do, I take all strings of x's and p's that are of length less than L. There are of order 2 to the L such strings. This gives me a 2 to the 2L of order 2 to the 2L dimensional matrix. I get a big matrix. I write down all possible relationships between these constraints. So they're mostly linear, right? These kind of things. These are linear relationships between operators. But then crucially, I'm going to use one more constraint, which is nonlinear, which is a cyclicity constraint. So if you have matrices, of course, in a trace, you can cycle them round, right? These are operators, so the cyclicity is a little bit more complicated, right? Because when you have to move the operators through each other, but we can deal with that. And then this is where we're also going to use large n. This is the only place the large n is going to come into it. Actually, we're interested in large n. So actually, unlike other numerical methods, this is not based around small n. It's based around large n. Because if I take n to be 2, 3, 4, I could try to just solve the thing numerically using a conventional method. But n equals infinity is harder to access with, just putting the thing on a computer. So for example, Monte Carlo studies of these kind of models that people have done truncate to some finite n. So this is n equals infinity. And what it lets you do is correlators, multi-trace correlators factorize it in n equals infinity, right? So it's something like trace p at infinite n, I can just factorize it like this, okay? So here's an example, right, where I've used large n to factorize here, actually also here. So this is a quadratic constraint now on these expectation values, all right? Good, and so what do you do? So you've got a big space of expectation values, okay? You've got a positivity constraint on these expectation values. Sorry, you've got a positivity constraint, you've got some linear constraint equalities, and you've got some quadratic equalities. And then what you'll find is that there's a continuum of energies for which, right? So there's some big space, right? And there's some, you're going to find that there's like a region a bit like this, that maybe that's allowed, okay, by all these constraints. And the energy takes a range of values, because the continuum of energies is not discrete. And actually that's what you expect, because at n equals infinity, there is a continuum of energies, okay? Because you have suitably normalized at large n, right? So at large n, I've got infinitely many operators in infinitely many matrices. If I just excite one of them, that's an arbitrarily small change in the energy. So you actually get a range, a continuum of energies. And so what we're going to do is do gradient descent. So this is like a kind of optimization problem that actually is very familiar, and not to me, but to people in general, which is a constrained optimization problem, right? You have a bunch of variables. We have some linear constraints, some quadratic constraints, and an inequality, an inequality. And so you could just do gradient descent within that constrained space to find the smallest energy, and we're going to hope that well, actually, so if we could find this minimum, that would be a rigorous lower bound on the ground state energy, because the actual physical ground state has got to be included. It's definitely allowed, and we might overshoot, but the ground state energy has to be allowed. So it's actually hard to prove that your gradient descent has actually converged. But if you knew that you'd found the minimum, then you would have a rigorous lower bound on the ground state energy. Okay, so just to show you that this works, again, one matrix is solvable. Okay, we're doing one matrix at the moment, and actually for relatively small, so these are different L's. Okay, so remember L was the length of the strings of operators we're considering. This is the energy of the lowest energy that we find as a function of G. And look, there you go. So I guess it does seem to be going to G equals 0 without a problem. So L equals 2 is not converged, but by the time you get to L equals 3, L equals 4 are basically on the same line. And this line is the exact solution that we know by mapping to free fermions. Okay, so this works. This is trying to show that it works. You also get the expectation value of x squared on this state. Okay, so as a numerical method, it seems to work, though there's not a theorem that it has to work. And actually, here, yeah.
Sorry.
Yes.
John, you have restricted to a positive coefficient for x squared. I mean, there's a phase transition in this model for negative coefficient.
Yes, these are very interesting. Yeah, we haven't, I mean, we've been thinking about this for, let's see, we've got all this, I mean, I've been thinking about these general problems for a long time, but anyway, Henry Lin's paper appeared just 3 months ago, and we got very excited about it and tried to generalize it to quantum mechanics. I think there are lots of things that we haven't thought about yet. Okay. But indeed, so I don't know, for example, what happens when you have like degenerate minima, and I just don't know if the potential looks a bit like this, and there are interesting phase transitions as you we haven't thought about it, and I don't know if there'll be subtleties in the spirit of the earlier question at non-analytic points and so on. I don't know. I don't know.
Okay, thanks.
Definitely. It would definitely be easy to set this up. I mean, these are not, actually our code is online, and that's definitely a question that could be addressed. Yeah. Sure. I mean, we didn't spend a lot of, go.
Can I ask a question?
Yes, please.
For example, take two canonically conjugate variables, x1, x2, p1, p2, okay? And consider the algebra they generate, call it A. Mm-hmm. Then you can also consider A tensor M2. M2 is a 2x2 complex matrices, which is your algebra. Your matrix is the entries in the original algebra that you were writing down before, right? You get a matrix like this. Okay, I'm not taking expression values again. Okay, this statement is that this 2x2 matrix is positive. So so this looks like a completely positive map from the original algebra to this algebra tensor M2. So it looks like a CP map. And there are results that these are completely given by this Krauss map, Stein-Springs theorem and so on in quantum computations. Isn't it? So
sounds great. I don't know, but look, if there's more sophisticated ways to phrase this would be perfect. I mean, let's see.
Looks like a completely positive map to me. Okay? And
yes, this is a map. That's certainly. Let's see. So we're mapping from. I agree with you. We're mapping
original algebra to say n by n matrices with interest in the algebra.
Yes, that's correct.
And you want it to be completely positive. Mm-hmm. If you take a positive original matrix, the image should be positive as well. Okay? Mm-hmm. those maps are completely characterized by what people call as Krauss map or Stein-Springs theorem and so on. I'm wondering why one cannot use it here.
Quite possibly, we have a very lowbrow approach, and it would be fantastic if anyone. So again, if you could write those references down in the chat, that'd be fantastic. Yeah. It's there's no sophisticated mathematics of what I'm doing, so it would be fantastic if it can be made more elegant. Yeah.
Paul, if you send the references to me, I will send them in an email to him.
I'll write.
Very good. Yes. So indeed, and also, it goes without saying the exact solution of these kind of matrix quantum mechanics does involve some rather elegant mathematics, and so it wouldn't be insane. There's a lot of structure here that we're not using very explicitly. So that indeed right. Very good. So yeah. Okay. So I wanted to show you one more plot here. Yeah. By the time we get to two matrices, it's a simple generalization of one matrix. So it doesn't. Yeah, we're in good time. So here I show you the energy works and the x squared works. And maybe to get a better sense of it, here's a different plot. Here's the expectation value of x squared as a function of energy now. And so the minimum I'm talking about is here. Okay, so that's what we've done. And so this shows you, but suppose I go above the minimum, right? Remember I said in the space of operators, there was some region that's allowed, right? And what we've done is we've gone to the minimum energy. But if we go away from that, you can fix the energy and ask what the range of x squared is, right? And so this here, from here to here, this is like the range of x squared that is allowed at some excited energy. And so consistent with the quantum mechanics and harmonic oscillator, the higher up in energy you go, the weaker your constraint becomes. But if you increase L, it narrows this region. And so, for example, what is a state with this energy that should be allowed? Well, it's the thermal state. And so the thermal, which is the give, actually, so for these, we don't even need energy eigenstates, actually, for this method here. We just need Gibbs states, so states that commute to the Hamiltonian. So density matrix rho that commute to the Hamiltonian is sufficient for everything I'm doing. So that includes the thermal density matrix, right? And so this line is the energy and the x squared of the thermal state, and we see that it's also allowed by this bootstrap. So it's conceivable that although things converge less quickly at bigger energy, it's possible that the thermal physics would also be finite temperature, highly excited states could be accessible with these methods. And that is actually related to the question that was asked a few minutes ago. I mean, there are interesting phase transitions as a function of temperature in these models, and they may be accessible. Okay, so what this was all meant to be was sort of confidence building. Okay, so now we take a step into the unknown, and we would like to say something about this theory. Okay, so this has two matrices now. It has a P, Px, Py, X, and Y. And we're going to allow a mass term. I mean, actually not super essential, but we can have it. And then there's a commutator squared term. Okay, so these are the kind of models that one is quite interested in, and they're not exactly solvable because the matrices don't commute in general, right? So you can't just diagonalize them. So yeah, I think that very little is known about this. Something that is known, there are some mathematical results. For example, something that might not be obvious, actually it's from a long time ago. If you turn off the mass term, then this potential has classically flat directions where the matrices commute. Because if X and Y commute, then this potential will be zero. And so you can go, there are lots of matrices don't commute. You might have thought there's not going to be a normalizable ground state, but in fact there is. The quantum mechanics lifts the flat directions. And that was proven in the 80s, I think, actually. So for example, there are results on this model is what I'm trying to say.
I think it's known as Jens Hoppe's model, if I remember correctly.
Yes,
and
right.
he's in the audience here. So
okay, thank you. Okay, so yes, again, apologies, yes, for lack of references. Good, yes, that's right. So who, Jens or Hoppe? Sorry. Yes, this was a PhD thesis of
Of Jens Hoppe, yeah.
Yes, Jens Hoppe, yes, sorry, yes, yeah, yes, sorry. That's right. So the massless, yeah, mostly in this massless case. Perfect. Thank you, yeah. So, but I believe that not much was known about the spectrum, certainly at n equals infinity. Very good. So now the strategy is the same as before, except that at length it's numerically more challenging, because at length L, they now be of order 4 to the 2L matrices. So as you increase the number of matrices, things are exponential in this length that you're considering. So that's why you can start seeing that going to 9 matrices looks challenging at the moment, but who knows? Okay, so to fix that a little bit, to fix that a little bit, we actually restricted. We got ourselves some more constraints by imposing a rotation invariant, actually more precisely that it's an eigenstate of angular momentum. This is absolutely not essential, but it just makes things converge a little bit. Which so this model has an SO2 symmetry. Has a rotational symmetry where you just rotate x and y, and this generates this symmetry, and we restrict it to states that commute with that. That just gave us a few more constraints, and not really essential. Now, just before I show you the results, because the answer is just not known, okay? We wanted to have some kind of benchmark. And so I think the benchmark was actually somewhat interesting. So I'm just gonna spend one slide telling you about that. So as far as I know, this is not solvable model. So we actually got a check, actually turned out to be a non-trivial check using a Born-Oppenheimer wave function. So you can do the following. So I'm just gonna make up a wave function, right? It's not an eigenstate or anything. I'm not clear. It works surprisingly well, but it's not a priori obvious why it should. Where we do the following: we diagonalize one matrix. Okay, so we have x and y. I'm going to choose configurations where x is diagonalized, and then y. Well, this, as many of you may know, this becomes xi minus xj squared yij squared, something like that, right? This becomes the distance between the eigenvalues of x becomes the mass term for y. And so then y is a bunch of harmonic oscillators, okay, with x frozen. And in the Born-Oppenheimer wave function, you just put those oscillators in their ground states, okay? And so that's this wave function. So you freeze, you have some wave function for the x eigenvalues, and then you put all the y's in their ground states. It's just an ansatz, right? It's not solving anything. And actually, Born-Oppenheimer rigorously gives you an upper bound and a lower bound on the ground state energy. You get an upper bound because it's a variational wave function. You get an upper bound because it's a variational wave function. That's standard. And you can also prove that you get a lower bound. This is well known to chemists. I think that they use this all the time. By just, so the energy, the 0-point energies of the y oscillators give an effective potential for the x's, right? Because as you move the x's around, it changes the energy of the y's. And so this effective potential, if you write down the quantum mechanics where you just have this effective potential for the x's, sort of integrating out the y's, you can prove that the ground state of that is below the actual ground states, okay? So given you make up a wave function, you get a rigorous upper and lower bounds on the ground state energy. And the nice thing about this is now this just involves single matrix eigenvalues, and those we know how to solve, okay? So this is a variational wave function whose energy still has a lot of structure, but it's a one matrix structure, so we can solve it, okay? So with that in mind, so then these are the results. So we have, again, the energy of our ground state. The method's the same as in one matrix, just they're more strings, right? Because there's P1, P2, X1, and sorry, right? So this I should have said. This 4 to the 2L comes because there's X, Y, PX, PY. There's 4, you have a string of length L, and at each point in the string, you can choose four matrices. So it's of order 4 to the, and then you build a matrix of those strings, so you get 4 to the, this starts to get quite big numerically. Right, so these dashed lines are the Born-Oppenheimer upper and lower bounds, okay? So I was a little bit surprised that they were pretty tight. And L equals 3 is this one, and L equals 4, which that's our best so far, is this one, and so that's within these bounds. And at the moment we haven't been able to. L equals 5 is quite big, but hopefully this is somewhat close to convergence, although we don't. So what we don't have here, like in this case, I'm sorry to go back, right? L equals 3 and L equals 4 are just on top of each other, right? So you know that that's converged. We don't know that this is converged yet, but it's within some bounds. And so once you have these bounds, then you can also get the expectation value of trace x squared. This is our best approximation to that. And then also you can get the expectation value of the commutator squared, which is this line. So something you can check here, for example, is that trace the commutator's expectation value of commutator squared. So you can write down something like this, but this does not go to 0 as g goes to infinity, right? So a very naive thing you might have thought, I mean, you might not have thought this, but some people have thought this, that you might have said, well, when g goes to infinity, the matrices want to commute to minimize the potential. Okay, that's a very classical intuition, and it's just not true. Okay, the matrices do not become commuting at large g. I mean, I think we knew that anyway, but that's something you can check. Okay, so we calculated these things, and so I think these are the most that we know at this point about this model at infinite n. I definitely think that these can be improved by, well, probably by improving the numerical method. All right, so just to conclude, the main point I'm trying to make is that these positivity constraints, it's a little surprising to me, but maybe after like some years of this bootstrap stuff working, maybe it shouldn't be too surprising. So positivity constraints give a powerful approach to matrix quantum mechanics wave functions. We got some new results for 2 matrix quantum mechanics. We think that we can go to more matrices and add fermions, especially with rotational invariance. So if you can truncate to if you only consider strings that are singlets under SON, under rotational invariance, that makes life much easier. And so, you know, the more ambitious plan that I definitely believe is accessible on a human timescale would be to really characterize the BFSS ground states. I think non-zero temperatures, I gave a hint to also should be also accessible. I didn't mention, but there is a large body of Monte Carlo results, including by people in Dublin, on these models. We're taking a more quantum approach to the ground states, but I think that these finite temperature results should also be accessible. Except we're going to have the quantum wave function of that, so possibly we learn something about black hole microstates. And ultimately, I mean, if one's looking even further ahead, I mean, in principle, we're trying to approximate the wave function, and expectation values are just one thing that a wave function has. A wave function has a lot more information, like entanglements, for example. And it would be very nice to get more fine-grained information about these holographic quantum states, like the entanglements. So I think we've really just gotten started, and I think there are lots of things that will be possible. Hopefully, maybe even there'll be some analytic stuff that could be possible too. All right, that's all. Thanks.
There is no sound.
Yeah, somebody. I can't hear you.
Yeah, I muted and unmuted everyone, but I think that everyone is back muted. If you have a question, you can either raise your hand and I'll call on you, or if you want to just, if it's orderly enough, we can probably just allow people to unmute themselves and ask questions. So thank you for a very nice seminar. If anyone has some questions, please.
Maybe I could ask, so are you using large N? Is that crucial for your analysis or not?
Yeah, very good. So the only it's being used. It's an interesting question. So it is being used here when we impose these cyclicity of the trace constraints, which do have a slightly different status from right and good. So you could ask two things. So you could ask, well, what if we just take out those constraints, right? Just don't consider them. And the second thing is, well, could we impose these constraints but not take large n? Okay. So using these constraints but not taking large n, that looks very difficult, because then we have to deal with these multi-trace operators, and that's just a much bigger, in fact, exponential, much bigger space that you'd have to be working in. So if we want to use these constraints, large n is crucial. I think that's not a bad thing, in the sense that it's sort of the opposite of small n, right? At least it's a complementary. For example, in some of these Monte Carlo studies at finite temperature, there have been disagreements about whether certain transitions are first order, second order, because you get different results for n equals 10 or n equals 30, right? And you want to know what the large n, so it potentially. Now, back to the first point, I don't know. Suppose we just don't impose, right? You could ask, suppose we don't impose this this constraint at all, how much will we lose? And as you can see, in this case of two matrix, maybe we should explore this for one matrix, which we haven't. But with two matrices, and we're really fighting. We're on the boundary of what's what was numerically possible with the computational power that we had sort of easily accessible and so on. And so we did definitely need them. If we were to take them away, where would the n? I mean, the model wouldn't even know what n it was at, I think, because there is just no n. Yeah, there would not be any n's anywhere. So it feels to me like you probably do need these cyclicity constraints, I suspect, to get it to converge, but we haven't. That's not a proof. Yeah,
thank you.
Yeah, that's my suspicion.
Let me ask you what the other complementary side of things, instead of considering two matrices, is to consider very large number of matrices. There you have an alternative expansion, which is called the 1/d expansion, where d is the number of matrices. I think it would be interesting to you can get some analytic results there. It would be interesting to compare the two.
That's definitely that's a good point. And so doing like a study, the crudest thing would get very hard with the number of matrices. But if you restrict to rotationally invariant configurations, the number of matrices kind of drops out. I mean, because you're just considering like the traces, the operators you consider would be things like, xi, xj, xi, xj kind of thing, right? Where all the indices are, where the indices. So I and j could run over 1 and 2, or from 1 to d, and it doesn't matter, right? So algebraically, with rotational invariance, large d might be doable, could well be doable, and indeed, in principle, one should be able to reproduce reproduce known results. That would definitely give a check on things. Right. So exactly. So suppose, yes, I agree. I mean, I don't know. So is this right? The game has two sides, right? One wants to go to new regimes that are not accessible with other methods, but precisely because they're questions of convergence and stuff, it's good to be well grounded in stuff where you know the answer. And so certainly, yes, large D, yes, I don't disagree with that. Yeah. Actually, I really had one more thing to say about the cyclicity constraint. Actually, just that numerically, there are not many of these. There are actually many more, at least in the case of these constraints and these ones. So they're not actually a lot of these constraints, but they may be the most important ones nonetheless. Yeah, it's funny thing. So yeah, anyway, but large D, yes, definitely. Large D in principle should be doable. And I didn't even mention, so that would be necessary for BFSS, for example. And fermions, of course, also are like more matrices, that they're not intrinsically different from you know, you have trace, you know, x1, x2, then there can be some size and some x's, right? You know, the fermions would just sit in the traces like any other matrix. However, supersymmetry does give you some, if you restrict to supersymmetric states, then they're annihilated by these Qs. And that might also give you, and Qs like the square root of the Hamiltonian. That there might also be some more powerful constraints with supersymmetry. And that hopefully you could hope that that's going to compensate, right? So adding fermions gives you, yeah, more bigger space to scan over, but with supersymmetry you also get stronger constraints. So I don't know, you could hope that that'll make it nicer, but I'm not sure.
Have you formulated a supersymmetric version? Is there a toy supersymmetric version that?
Yes, we're thinking about that. Yes, that's what we're currently. I've been thinking about the last few weeks, and there is this Marinari Parisi model. I think that's what the name. So that there is a one matrix with a fermion, and actually that we just solved. Yeah, that was almost too easy. So that did work, but it worked like actually we just almost in closed form in fact with so that's one boson and one fermion. So that's like the generalization of, there's a supersymmetric generalization of this model, and there actually this, yeah, imposing supersymmetry turned out to be very powerful. Wait, am I lying? Okay, I can't. Yeah, this is just from last week, so it's a bit, it was in flux still. But yes, there is a simple model that could be thought about for supersymmetry. Yes. And what we're hoping, I mean, what I think might be possible is that the supersymmetry is sort of enough to get rid of the fermions, and so that you can just map it onto some boson problem. Probably that's how it's going to go. That there might be some
trace out the fermions.
Well, not basically somehow relate every trace very, very heuristically, relate every operator with a fermion to one without fermions, sort of roughly using supersymmetry or something like that. And then, or there might, yeah, but it's still in flux. But yes, there are toy models with fermions, and I hope, and I think that I hope they can be solved.
Now with the conformal bootstrap, you're using reflection positivity, right? That's one of the key things. You're not using it here, but you still have it actually.
That's interesting. Yes, then maybe there are some more. Let's see.
May not be very useful, but
yes. Let me. I not thought about. Yes, I. Yeah, because right. Yes, yes. So good. I don't know if this is exactly related, but you could. All these are sort of time independent states, and you can actually also think about time evolution. So meaning inserting operators at different times, right? So all these operators are inserting at the same time, and however, unfortunately, time, right? So time evolution, is just conjugating an operator by like something like this, right? And this rapidly becomes a very long operator, but there may well be things related to time evolution that are useful. In fact, I very much hope that these methods can be greatly improved with more constraints. Yeah.
Can I make a small remark? By the way, the seminar was really good. I enjoyed it a lot. Okay. But I want to ask you a question. You probably know that if one is given just the cyclicity of the trace or the state on a string of operators, just the cyclicity, then one can derive recursion relations which relate successively the 3-point function to 2, 4 to 3 and 2 and so on, and solve for all of them. It is called, I think, it comes in this free probability theory. Okay. The free probability theory. I have an impression that this kind of matrix model you are discussing have been discussed by Voiculescu and also by Gopakumar and Gross. Are you aware of this work?
Yeah, I think my suspicion is that these probably involve matrix integrals rather than matrix quantum mechanics. That's and that there is these p's are what make the difference between them. These p operators instead of just having x's.
No, they don't make any difference. The theory, Voeculescu theory is just for any operator, C-star algebra. So, but the probability, the free probability is defined by saying that the expectation values have certain properties, which is true normally, but much weaker. Basically, it involves the cyclicity of the trace, okay, and some other condition. Okay. So it doesn't care whether you have p's and x's or whatever. Okay. And I think my remembrance is that Gross and Gopakumar and Gross use this, and along with something called the Kunz algebra or extended Kunz algebra to solve large and matrix models.
Yeah, I think
and also Voeculescu's review does it. Okay? Voeculescu review on free probability theory does it. Okay? It may be, I think it is related to, maybe of use to you. I don't know.
Okay, I'll take a look. I mean, I'll be definitely will take a look. That this is all very useful, and thank you for
that's okay.
Mentioning all these points. Definitely, I mean, most of the sort of exact results that I'm aware of tend to involve one matrix, but it would be fantastic if there's stuff that works. And I'm definitely not an expert on the more mathematical side of all this stuff. So I'd love to learn.
Can I ask a question more on the physics of it? The model that you considered there with this commutator, this Yang-Mills commutator, it arose as a quantized quantum deformed version of a membrane.
Right.
Can you see any hint of the membrane in this?
Yeah, very good. So yeah, I mean, that is the question that one would like to go to, right? Because that is the sense of emergent space, right? It comes back to, right, that the membrane is a space, right? Actually, I can, let's see. Right, so let me see. What do I want to say? We haven't all got to that yet. Is the bottom line? I think that to really, how to say, the fact that, I mean, I think supersymmetric versions of these models are going to. So the fact that these there's not really a sense of emergent commutativity and stuff. This is probably quite a quantum. If there is any geometry in this model, I suspect it's quite a quantum one, meaning that fluctuations are large. I think let me tell you. Okay, I want to say two things. I think supersymmetry is going to be quite important for the geometrical picture. So there's another model with 3 matrices actually that we solved in another paper using a different approach that I didn't have time to tell you about today. We have 3 matrices, and those 3 matrices have a fuzzy sphere ground state, right? So that there's a model a bit like this one, where the classical potential is minimized on x equals I, y commutator z, and so on, right? And this defines what's called a fuzzy sphere at large n. This is SU2 algebra, and there we could that's like a membrane, right? Also,
yes.
Right? Because and so yeah, those are things that one could hope to look for when there is a classical geometry to find. I'm not sure that this model is going to very directly give you a very classical geometry, but yeah, definitely that's where one would like to go. I mean, I think we're still developing the tools, but let's see, what can I? Let me say that yes, I have nothing to say about geometry in this model at this point, but that question will be answerable. Yeah, but once to take a model where there is geometry, and supersymmetry really helps because these otherwise the quantum fluctuations are quite big, and supersymmetry tends to damp those out, and you're more likely to get like a moduli space of eigenvalue, some macroscopically large emergent geometry that it makes sense to probe that has a sense of locality. And what can happen otherwise is that the quantum fluctuations, the fuzziness is sort of the same size as the geometry itself in some well-defined sense, and then you don't really have a notion of locality. Actually, I'm not. Yeah, let me leave it at that. But with three matrices, there's a bosonic model that does have this fuzzy sphere geometry, and yeah, that could well be accessible with these methods, I think.
Mm-hmm. Very good. Are there any other questions? We should probably, if not, let's thank Sean again for a very stimulating talk. And I will stop the recording.
Okay. Thank you.
Thank you.
Thanks.